So it's my great pleasure to welcome Professor Saman Amarasinghe from MIT. Saman is one of the world-leading scientists in compilers and systems. And together with his group, he has been developing and starting a bunch of super influential projects like Petabricks and the raw architecture projects and many, many others. He's also a successful co-founder of a bunch of deep tech startups. So it's really a great pleasure to have you here. Thank you for coming and looking forward to the talk. to the questions. Also to the questions.
Okay, so I'm going to talk a little bit of a different approach. This is mainly about performance type issues, and probably we start some of these problems, and hopefully later in this trajectory, we'll get a lot more into things like security and other aspects in there. So today I'm going to talk to you about supporting structured data. If you look at the world till now, it's mainly built for dense data. If you look at modern architectures, they can do amazingly well in things like matrix multiply. You get 80% performance of GPUs, CPUs, and last 50 years, architects went crazy building all these things in the machines that take advantage of this kind of dense data. If you look at programming systems, even the first programming language, Fortran, supported arrays. From that onwards, dense data, dense arrays have been supported very well. We build languages, perform optimizing compilers, all these things to support dense. Great. If you have dense programs, we do really, really well. Still, there's a little bit more to do, but we are mainly there. But if you look at the world, most of the data out in the world are sparse. Or have structure. So for example, if you look at a point cloud or graph, it's a lot of sparsity in there. If you look at things like these videos and these MRI images, there's a lot of repeated value. It might not be zeros. If you go to sparsity, it's a lot of zeros and other values. In these like videos, there are a lot of repeated values. They're not zeros. So these can be compressed in there. And also, a lot of interesting data symmetry. So now, how do you support this? This is a very interesting domain in here. So let me go into one side of that we have worked a lot, sparsity. Sparsity is everywhere. So in data analytics, in a bunch of new stuff, machine learning is getting sparsity. Even things we have been studying for the last 50 years, like science and engineering, a lot of data is sparse. To give you an example, in data analytics, okay. Data analytics in here. Here's Amazon, basically product review. It's a three-dimensional tensor. For every product, there are a bunch of reviews in there. You say every people who have reviewed the products, and also all the words used in the reviewing the product in here. So you can look at this as the three tensor in here. This is extremely sparse. If you try to represent this as a dense matrix, the Amazon data center don't have enough space to keep it. But if you just keep the non-zero values, it will fit in your desktop. So this is the kind of sparsity in there. So sometimes it's not even possible to keep these values, not just simple optimization in here. So sparsity matters a lot. The other interesting thing is, if we treat this sparse data and keep it dense without thinking about sparsity, you are losing performance. So what we are showing here is matrix multiply, where it doesn't matter. It's all dense array in here. What the sparsity level is. And sparse matrix vector multiply. This sparse matrix vector multiply. What you see here is, because to deal with sparsity, there's a little bit more complexity you have to handle. The code is more complex. So up to about 65% of density, your matrix vector multiply wins. But at that point, after that point, it just basically becomes a liability to keep multiplying all those zeros, and the sparsity start winning in here. So interesting thing in here is, if you go to matrix multiply, the curve is a little bit down there. So you need to have more sparsity to win in that game. But the interesting thing is, if you look at the sparsity pattern, this is the SPME pattern and SPMM pattern. I guess I can use this one. So neural networks kind of sit around in here, sparsity in here. So they are barely like, okay, can I take advantage of it? Probably I just keep dense is good enough. So people are hedging the bets. But in that corner, there are a lot of interesting applications. Where sparsity is in huge numbers. So things like fluid dynamics to graphs, a lot of internet social graphs and stuff like that are hugely sparse. There you have no option but to take advantage of sparsity. So the interesting thing is, sparse code is not that simple. So here's a simple 3 tensor multiplied by a vector. If it is dense, you write this code. A freshman in a college will be able to do that if you use this as a problem set in here. But now, if you make this 3 tensor basically sparse, you write a little bit more complicated code in here. On the other hand, if both are sparse in here, now the code gets very complicated in here. So if it is a compressed format in the vector also. And if you change the vector format to something like hash map, more complicated code, but very different. So now writing this code is not that easy. You have to keep writing this code in here. But now, if you want to write this 2 different 3 tensors adding in 2 different formats, to get the best performance, you need this piece of code. I mean, trust me, Intel, to do their MK library, has hundreds of engineers all around the world writing code like this. Great opportunity for employment. So this keeps a lot of programmers jobs, but there is no fun code to write. So it would be nice to generate this code. So one way to do this is write libraries. The problem is, if you look at different areas, there are a lot of code that you need to write libraries from. It doesn't scale. Even if you look at something like vector matrix multiply, SPMV, IGEN has this implementation, and every different other parts have small variations, because the small variations like adding a constant or scaling it, if you do it and generate special code, it's much faster. So you do that. In fact, OSCE has 282 versions for that code alone, that small computation. Different size, different sparsity patterns, all those things come in. Why? Because dense matrix, there's only one representation. If you look at sparse matrix, depending on your data, your thermal simulation, web matrix, finite elements, you have many, many different representations that you can use. Each representation works very well for that type of data, and it doesn't scale that well. So these have this representation, and of course, where you run. So this is why you have full employment if you're a programmer, to keep running all those kind of versions. This doesn't scale really well. So I talked about world built for dense. How about sparsity? If you look at architecture, the current architectures are so bad in supporting sparsity. So if you look at something like this is using PageRank about cache misses versus dense matrix multiply. PageRank at 40% cache misses, barely using the web processor, really, really inefficient in here. So this is one project, even though I'm not going to talk about. I think architects also have a huge space that they can improve, because they have improving dense stuff. They have to do a lot more work to get the sparsity code hard. So the architecture is also not that good. How about programming systems? What abstraction? If you want sparsity, you have to write that code by hand. There's no nice large system to do it. So this is where the world is. So what we did was we built this system called the Taco compiler, sparse tensor compiler. What it takes is, it takes an expression of your code using Einstein notation. It's fun to basically cite Einstein in our research. So Einstein came up with this notation to represent when he did his early work. Then we can come up with a format language to describe the formats of each tensors. And also scheduling language to give some hints how you want to optimize it. And I'm going to talk about this later. And then what I'm going to do is, given all those things, I can generate right now C and CUDA code in here. Then also I'm going to talk a little bit about this new addition we are doing. We are having something called a Looplet language. And then it can go beyond sparsity for other kind of structured patterns that we can generate code for. So before I go explain those things, I want to show a few things in here. So interesting thing in here is, if you do this, we can get really good performance. The problem is, There's no system that can generate all possibilities, but there are people who had handwritten few kernels by hand. So if you look at those kernels, we are getting really good performance in here. Here, low is better. So Intel MKL is probably the standard, and we are generating code that close to that standard. And this STDMM, we are getting close to the best code out there. And this MTT KRP also, we're getting code best performance in here. Interesting here is one thing you'll notice is there's a huge disparity between some systems and what we are doing. I want to address that issue. This is an interesting thing that is not showing up in dense. So if you look at something like STDMM, okay, let me switch back a little bit. If you normally go to dense code, the way people do libraries is they come up with binary operators. Multiply operator, add operator, stuff like that, and you basically cascade these operators to do much more complicated forms in there. It's not the best for cache utilization. You lose a little bit, but you can get good performance. That's what people using NumPy and stuff doing today in basically. You have these single operators that you cascade, do more complicated things. In sparsity, that doesn't work. I'll show you what. So here's this system called sample dense matrix multiplication. You take two dense matrices, you multiply them together. And if you multiply in here, you can get the very good handwritten code and really good performance in it. So in this one, you get 64 in a product. And then you are multiplying it with the element-wise sparse matrix, multiplying the result in here. So if you want to get this value, of course, you want this value calculated. But if you want this value, it's 0. So what we are doing is you calculate 64 inner products and throw away 54 of them and 10 survives. So if I knew that I only need these values, I don't have to calculate everything. So these people, what they did in here was basically they composed different things. We got a really fast dense matrix multiply and then composed in there. But they're losing big time. If you come up with the entire problem and solve it as a one unit, you can get a much better performance in here. So this is why this is much harder to get good performance than basically dense code in here. Because there's asymptotic win in here if you do it right. So we basically can generate that. So what I'm going to do today is talk about challenges in these 5 different things we have worked on, and give you a kind of a little bit of a very high-level glimpse on how we can go automate this part in here. The first thing we can do is irregular data structures. And we came up with a thing called a format language to deal with that. So let's jump into that. So first, I want to describe what a sparse data structure is like. So what happens is I have this 2D matrix, and only values, real values are in these gray areas, letters. Others are zeros. So in traditional, I can represent it in the dense array. Great, very simple. I can access anything, I can calculate. So this location is, I can easily calculate this location in a formula and get there, and vice versa. But it's very inefficient. I have all these zeros stored, I'm wasting a lot of things, and if you have a lot more sparsity, this is not efficient. So I want to get rid of zeros in here, and I represent that. So now I only keep the non-zero values in here. Now, but how do I know what the hell that value is? So I need to keep some additional data structures. So here's one way I keep a row and column coordinates. Now, given the data, I can look at the coordinate value and I know what that is. And I can go vice versa, back and forth. And again, people realize there are a lot of duplicates in row because there might be same row has multiple things in here. And you can compress this, and this is a very common format called compressed sparse row format. There you can say where the columns start, so you can have a much more compressed row format in here. And then the columns will point out what it is. And if you get a more complicated, this 3D structure, data in here, 3 tensor, you can have this very complicated representation representing this. But what we realized was there are each of these representations, like compressed sparse fiber is a paper. It's a very, very well-cited paper. People come up with a new representation, haiku representation, new paper, great. But what we realize is each of these representations can be broken down by dimension, what you do to each dimension. So this dimension basically slices the coordinates, it's a dense dimension. This keeps the rows, and this keeps the column coordinates. And then if you come up with different, what we call level format for these things, I can describe many, many different combinations in here. So if you look at dense, compressed, and singleton, This is this matrix in here. So if you put dense for outer dimension and compress for inner dimension, this is the CSR representation. If you put compress for outer dimension and a singleton that is only one element in for the next one dimension, this becomes what we call the coordinate format. So by doing this level format, what we can do is represent not only those two, many other interesting representations can be done in there. So everything is a paper, and we basically describe a common way, a language that describes all those things. And then by adding 3 more of these level formats, we can more or less get most of the interesting formats out there. So what we did was, instead of coming up with each format their own system, we have a language that we can describe this level using level formats to basically get all these representations. So this simplifies the compiler's life very much. So let me take you a little bit beyond sparsity. So assume this array in here. So if I do compressed level for CSR kind of representation, that you probably didn't see the color, so I don't get the zeros in here. I have to represent every other value. But if I look at this thing, I say, there are more ones than zeros. So why does you just elide the zeros? One can say, okay, skip ones. So if I say fill value is 1, I can say, instead of skipping zeros, I just skip 1, I get this representation. So it's a little bit more compressed than that. But that you will wonder, there are a lot of runs of zeros and ones. So if I basically do run length encoding in here, why doesn't it? Okay, here we go. So what you can do is now, what we can say is, instead of just representing zeros and ones, you replicate the last value how many times in the next gap in here. So by doing that simple extensions to this, we can actually get run length encoding too. So the idea here is you just take the sparsity from sparsity says, if I have gap is 0, fill value says the gap is the fill value, run length encoding gap is the last value you saw, just fill the gap out of that. So by doing that very simple extension, we can actually get run length encoding in here. And in some sense, the very interesting thing is sparsity was developed in a very different community than compression. And if you are doing interesting thing about compression is they only mainly worry about data storage. Sparsity people mainly worry about computation. We can bring them together. We can give the computational benefits to people actually thinking about lossless compression, so which is found very interesting in here. So this is really cool. What we can do is things like, these are different representations here. This is edge detection on MRI images. So we have pretty good size reduction. So so this is no size reduction. This is in there. And then for go to different versions, we can get huge size reduction in here. And also, you can get some speed up out of that in here. So these are almost 2x faster in here. The OpenCV is a handwritten implementation on dense, very well managed in here. So we can even do better than that by just basically, because when you have sparsity or run length encoding, I can actually reduce the computation. I'm doing less work in here. Whereas OpenCV did a very good fast implementation in that. Same thing in things like alpha blending of 2 videos. As we go to different representation, you can get better and better compression of data. Run length encoding gives a really good fast implementation. Sparsity did there. LC77 gives a much better compression, but it doesn't give you that much speed up. So a lot of cool stuff you can do in here. Okay? And another push we have done is dynamic sparseness. By the way, I'm giving you this very high-level overview, just flying through a lot of interesting things. If you have interest in any of these things, come talk to me afterwards. So in here, the interesting thing about these tensors are you can operate them in very fast. In dense tensors, inserting element is order 1 because all the elements are allocated. You just have to you take a value out and put a new value in here. Deleting element is the same. You just take a value and make it 0. But sparsity, I only store non-zero values. Now if I have a new value in here, normally I have to copy the entire matrix out and expand that. That's not that cheap. So There are a lot of interesting places there, things like dynamic graph processing, sparse neural network tracking, where the sparse tensor keep changing. You keep adding and eliminating elements. And this is very, very expensive in here. So what we need is a pointer-based recursive data structure to represent that. And we have this novel way of describing this pointer-based data structure and automatically generate this thing. So what we have is that is a linked list, bucket linked list, all these different type pointer-based data structures we can basically describe using this language and auto-generate basically iterators over this in here. So now you can do a lot of cool stuff in here. So this is very interesting. So that's basically data structures. Another thing about sparse data structures is it's very hard to iterate over them. There's only one way normally you can iterate over them. If you try to question?
Yeah, one thing I just, I guess a couple things curious about. One is, you showed this mostly with integers.
Yeah.
But there's also innovation on representation of scalars, like block floating point or different number formats. Do those compose in general, or do I need to be aware of the scalar representation to exploit?
No, I think it composes in there. But one thing very interesting that can be is variable size stuff. So a lot of times, certain areas you want much more precision, others. That is, I think, interesting problem we haven't gotten into. I think because here I can deal with this different size, like zeros and non-zeros. But I might be able to also deal with variable sizes if I play that game right. I haven't figured out something like that. But I think you can. But if the fixed size, different data types, I can deal with that easily. But also, yeah, floating point 0 is a little bit of a misnomer, whereas integer 0 is very clear. So iterating of these data structures is very interesting and give you some unique stuff here. Let me express that. So assume I have this compressed storage format in here, and these are different levels that goes to the bottom in here. So this is how the graph is connected in here. So there's no way I can do orders one random access in here. I have no idea if I access, I have no idea what this is. So I have to go iterate over that. If you want to access that thing, if you want to locate 202, I have to start with the first person, go find 2, go find 0 in here, go find the range in here, go into that, find that, and find the element. So there's a order of you have to go through that. Every way you store this data, give you one order that you give the very efficient access. Any other order, you have to search and do binary searches and stuff, very expensive. So what this says, you have to do IJK order in here. So if you are doing a simple computation, like 3 tensor multiplied by vector, here's a 3 tensor here. If you're dense, you represent this is a dense value. This one tensor, this vector, I can replicate it into 3 dimensions in here, get something like that. My iteration is very simple. I iterate over these 2 by these indices and basically do the computation. I can bring those 2 together on top of each other, iterate that. Sparsity is a little bit more complicated. So if you have a 3 tensor in here, the way it's stored, you have to do IJK. You have to iterate over that order in here. Otherwise, you don't get that. And then in here, I have to do this K in here. And now if I want to bring them together, I can say that K I iterate like this. And then in here, I am doing a union. Sorry, intersection. So only intersection survives. So when I iterate within these 2 of them together, I have to do intersection in here. And then output get produced by this INJ. So that basically is a nice representation of what this computation, if it is sparse, how to do that in here. What we can do is we can mechanically generate these diagrams for every complicated Einstein notation expression. That will give you the ability to how to iterate over those things in here. And of course, if you have some, like if there are switch dimensions, I will get a cycle and say, okay, no, there's no easy way to run through that program also. So by doing that, I will give you kind of a roadmap how to run through this program in a very mechanical way, can generate roadmap. And next, I will show you how to use this roadmap in here. So if you have something like A dense, B dense, compress, and C compress, and A is output, I am doing this operation in here. I can go to first level and say, aha, I only do 1 dense, I know how to iterate over dense in here, very easy. Next one I say, I have one compressed B. I know how to iterate over one compressed dimension. It's a level dimension. I can generate code. When you go here, I have a little bit of a complication. I am doing a merge dimension. B, which is compressed, C is also compressed. I have to iterate over that. So this is a complicated thing I have to iterate. And then finally, inside here, the computation goes, what you have to do that. So one thing I want to talk about is how to generate something when you are doing this kind of co-iteration of multiple parts in here. So this is my third part. Avoiding wasted work when you are doing co-iteration, what we call co-iteration code generation. This is where we get a lot of interesting savings. So assume I am doing just two simple vector multiplications in here. And multiplication is just intersection. So if you have a bunch of elements in C and bunch of elements in B, only thing that cares about is intersection elements. So what that means is we have what we call lattice in here. We have a B and a C. And while B and C there, I have to generate. And when I am done, I am finished in here. So B and C says, iterate while both B and C have values. And go to the next value that both has. And keep updating. This is what we call a two-finger merge going through there. And you generate the code when there's a value with both B and C has the same index in here, value for that. And then otherwise, I just skip over everything. And if either B or C runs out, I'm done. I don't have to do any more work. That's great. On the other hand, how about addition? When you do union, you can basically get only B, only C, and both B and C are present. All there are three cases in here. So this is a union here. Union can be computed as an intersection when both are present or only one is present in here. So this can be viewed as this simple lattice in here. So both B and C are present, only B, only C, and nothing. So first I go to BC and say this basically iterates while both B and C are available. And then the lattice underneath generates the code in here. So if both B and C are value is present in there, I do that. If only B is present, I do that. If only C is present, I do that. And this will give you, while I'm iterating over when both B and C are available. But if assume you C runs out, the minute you C runs out, you only have B. I only have to iterate B and produce B. And if C runs out, or C runs out, do B. If B runs out, you only iterate C. Very mechanical way to do that. But the beauty of it is, if you have something lot more complicated like this, if you are doing adding three elements in here, now I can just create this lattice and go to all these lattice points and keep generating code. And I can basically get the optimal iteration code in here. Even more interestingly, if I do something, assume I have D is dense. If D is dense, D is everywhere. So that means the graph changes to this one, because when D runs out, everybody runs out. And that immediately creates a much smaller piece of code because of this lattice changes out of that. So we have made these very complicated things that engineers spend weeks figuring out, just very mechanical. It just gets generated out of that. So that's really cool in here. So this is only doing intersection and union. But also we can do a lot of other things. All the other operations like exclusion, XOR, all those things are possible. So assume I want to do this addition code. Instead of addition, I want to do XOR. At that point, what that says is, when both B are present, I don't have to generate anything. So only this value has to be gone. So otherwise, I generate the other parts in here. So again, I can expand this lattice to do this thing. And in fact, we came up with a user-defined functions where you can come up with these very complicated functions and say how it's iterating over the space, and we can generate this code. So you can expand it to anything in here. Okay. So now I want to switch gears again and go into co-iteration over complex data. So far, we only dealt with sparse data. Sparse data is great. But as I showed you, world goes beyond sparsity. So what we came up with this new notion called a Looplet language, where you can basically combine a lot more other complex data beyond sparsity. So let's look at that. So if you have a dense array, the way you go through that is just incrementing, 1 by 1 by 1, very simple, I++, you go through that in here. And if you have two dense arrays, it's still the same thing. This is why Fortran and all the things we have done, CFI is very simple, because you go increment both arrays and you calculate. If you have 2i+1, then you have to do still incrementing by 2. Very simple. Having n arrays doesn't make life that much different. Now I assume a compressed array. There you go to the next element, next non-zero element. You jump over the zeros in here. What Taco originally did was, if you have a dense and compressed together, if you have dense and same, if you have a dense and compressed, what do? You basically iterate over the compressed array, next, and then you can look up into the dense array. So the minute I go here 5, I can easily order 0, go to the 5, because I know exactly how to calculate and go there. So I don't have to iterate over something, I can do that. So I can look up and go there. If you're dense compressed or compressed, let's do that. If both are compressed, this is where you have to do a two-finger merge. You have to jump over each of these things and, until you find common one and do that. So for there, you do a two-finger merge. So this is when you have dense and compressed. How about you have a lot of other things in here? You have many other representation things like run length encoding, block representation, variable blocks, pack bit representation, ragged representation. There's so many different representations. So the complexity of this is now going to blow very hard. So this is where we came up with this interesting language. Instead of saying all these n squared pairs or n cubed parts, can we, for each iteration, describe it using certain set of properties? Look up, run, we came up with this 8 ways of doing that. So assume I have this array in here. We can say we run over the zeros and you do a scalar, and that's called a spike. And so run and a scalar coming together is a spike. And if you have a bunch of same things, it's a stepper. And different things combined through a pipeline. So you have different ways of combining the data in here. And now, with this, what I can do is I can describe any complicated data representation using this language. How I'm iterating over data. I'm not doing the same thing. I'm doing these different things depending on the data. And then start generating code. So generating code for one is very easy. You look at a run, I have a pattern for run. If you have lookup, I have a pattern for lookup. I have front pipeline means all those things together, and stepper means you have put a loop around it. I can just generate code very nicely for each of these patterns in here. And then to co-iterate, you have to merge these two patterns together. And we have a bunch of rewrite rules to simplify what we can generate in here. And the nice thing about this is all these interesting, very complex patterns like ragged matrix, run length, and symmetric matrix, we can generate out of this thing. So previously, all these different patterns was a different paper, different compiler, and you had to choose your data. Am I going to use run length or I'm going to sparse? Now I can do everything, and so I can get a multiplicative effect of my data. If it has some sparsity, some runs, I can take advantage of everything, and now some symmetry, all those things in together. So we can have hybrid formats, and also we have a more interesting language. We can even come up with new formats. So if you have a data which has a funky pattern, we might be able to describe that and incorporate that into our compiler. So that's how we are doing basic expanding beyond that. So finally, I'm going to talk about optimized parallelism and locality in here. So I'm doing very well on time. You guys will have a good break in here, so which is good. So I'm not going to slow down. I always speak fast. Question?
Small question. Do you also support stencil computations, like with compressed formats that you described? Like all these sub-areas that you calculate in streaming fashion?
Stencil,
like sub-arrays over like a larger array? And
yeah. Because you can think about a multidimensional array or something like variable blocks is like that. You have different sites in there, and inside that you can have another pattern, stuff like that. Yeah. You can build arbitrary complicated. We haven't.
Also, you have the basic language for streaming computations from what I see.
Yeah.
Like you have the basic blocks for filter, map, fold, take, infinite. So essentially, data flow stuff.
Yeah, I can do that too. Yes, yes. We haven't gone there yet, but I think the language will be able to support some of these things. The thing about streaming is multidimensional streaming is very interesting because how do you deal with that? I mean, you can probably infinite on one dimension, non-streaming others. Question about that.
Yeah, so something for the format part, go back to there. I wonder whether you can learn a good format.
So, in fact, a part I'm not going to talk about here is, given a matrix, if you give a dense matrix, there's a bunch of work to figure out, machine learn, what's the best way to run a computation, what's the block, parallelism, vectorization, stuff like that. There's things like Halide has this paper, so okay, we can learn that. Thing about a sparse matrix is, there are so many representations, it's not the size. The dense matrix size dictates the computation. Sparse matrix, what's inside there. So what we did was, this matrix are very complicated. I don't know what the hell is going on. I said, can we treat a matrix like an image? And send the matrix to a convolution neural network. And feed it that to it will extract some features and feed it into my system to figure out the right format and the right way to compute that. So we have this system in there that basically because using the sparse convolution of the matrix and get the features out of that and features of the program. And we have a cost model, and we learn the right representation as well as the right execution model. Should we block it? Should we vectorize it? What dimension to parallelize? All those things are learned, and we get really nice results. Because sometimes one thing we haven't done is do kind of sub-patterns. So you can say part of it is one representation, another part. But entire matrix, dimension by dimension, you can come up with many different representations. And so that's a really cool thing we can do. And that's only right now we are doing it for dense and sparse. But when you go to these variable blocks and stuff like that, we might be able to do some really cool stuff in there. Yeah.
So by nice results, what do you mean?
So if I assume matrix vector multiply, so for certain matrix, we can get 2x on MKL. Because we can have a funky matrix, we have some banded, weird matrix. We can come up with a representation and iteration that blows out the general SPME code that do. Most things we just kind of match that because most patterns, I think the generic thing is good. But for special things, we can do really well. For example, if you have blocks, if you know you have 4x4 blocks, and we can take the blocks out, do a dense computation within the blocks, and do the rest sparse. Very good. Very good speed up in there. Any other questions? Okay, so for parallelism and locality, we came up with a scheduling language. Scheduling languages are not new. In Halide, the entire premise was we come up with the algorithm language and scheduling language, and we can get really interesting things. So we took on Halide scheduling language, and we said, okay, this is great. Can we schedule these loops? But there were some interesting things we had to deal with. So one big optimization we do in scheduling is blocking. The problem with blocking in sparse is how do you block? So what you can do is you can take your coordinates and say, okay, I'm breaking the coordinates by half. So if you do that, you get load imbalance because half the data might be that side, other half is in here. Other thing is you take a position space blocking. You say, okay, I am just blocking not in the coordinate space, but half the data in load balance data. But of course, if you do one dimension, you don't get best position. To get the best position, you have to do an interesting cut in here. So some dimensions might be, upper dimensions might be cut in a weird way in here to get the best position in here. So you have this interesting thing that we have to add to basically get load balancing in here. So I hope you can see this code. So here's a code that to do sparse matrix vector multiply in here. So this is just original code. And then you can say fuse and do position space mapping, and you generate that code in here. And you can say, you see where it's going. I'm splitting this into 3 different dimensions and mark them block, warp, and thread. You know where I might end up with that. And reordering that, I can generate code there. Then add a few additional things, say parallelize for GPU, block, warps, and threads. And suddenly it will generate this code with also call to the kernel in here. And also within GPU, I can also give additional things in here to basically pre-compute certain values, unroll certain values, so I can do all these crazy things and get really good performance. And MKL, trying to match performance was not that bad. We were surprised how well we can do. But going with NVIDIA and matching their handwritten kernels was really, really, really hard. They do crazy things to get performance. So we are... still, we are not completely beating everything, but we are getting close to in here. By doing that, we can basically, if you look at our representation in here that is in red, we are doing pretty well in many of these cases in here. In doing SPME code in a V100 and this MTTKRP code in here. And so this is really cool. We can get a really good performance in here. So we have released Taco in 3 different forms right now. One is C++, so you can just express the format. We can basically say what the data is in there, and then just write the simple expression by overloading. It will do and compile the code in background, link it in, and assemble the data and run in here. We have also incorporated that into Python in here. You can do PyTaco. And also we have this online code generator, which is really cool. Like a bunch of people have used it. So I think certain people tell us that they basically generate the kernel they want, cut and paste into their code, and they can run it. So you can come up and tell what kind of expression. You can type your own expression, select basically the pattern you want to generate, the sparsity in there, and you can generate code, and it will keep generating the code in here. So this is different piece of code. Let me run it for a little bit. So as we generate more and more complicated things, So we can do that. So this is really cool, fun online tool we have, and we are gathering data to see what people are using it to. It's kind of fun to see what people use this thing for. So this is available in here. So another interesting thing we have been looking at is Python. So Python has this, between NumPy and SciPy, there's a very nice interface for dealing with dense arrays. And people obviously say, okay, I want sparse arrays. SciPy has gone a little bit sparse. But there's this system called PyDataSparse that was trying to take the NumPy SciPy interface and do sparsity in here. But they had the interface, but they are generating really bad code at this point. And so what we can do is we can do almost 2 orders of magnitude better performance sometimes compared to their code in here, because we can generate really fast code in here. So we are actually trying to work with them, trying to get right now Taco into the Python ecosystem. So we have done a lot of publications here. So if you go to our webpage, you will see a lot of these things are one publication. So I'm going to go a little bit of a tangent because I have some time. This is what I hate about modern research, because every large project has 10 publications, and 10 years later, you're like, how do you know the project? There's no one paper. In good old days, if you want to learn something about Ethernet, there's one paper. If you want to learn about a system, there's one beautiful paper that you can read, become in there. And right now, so if you want good luck, there's so many things. And worse, the third paper is going to contradict the first paper because we keep learning in there. And then you assume a bunch of things, so you can't even read the last one. They'll assume so many things in there. So that's my tangent in here. We are doing a lot of new things at this point. Fred, who was the initiator of the project, is now at Stanford. He's pushing into many different interesting spaces around here. He's trying to combine this with like relational algebra and generate a lot of code generation in here. We are pushing into a lot of novel formats. So the way I look at that is, if you say in a database, if you want to do, we'll say a payroll, there's only one payroll schema. You have to use that. People go, it's crazy. I want my own schema in here. And right now, that's what we are doing for sparse data, all this data. There are few known formats, and you have to fit your format. How about for your data, you come up with your own format? And we can do that. So we want to push a lot of these things in coming up with these new formats in here. Try to figure out faster computer, more compact, many different types of structure. Can we deal with that? Like things like all these symmetric data, so can we do that? What that is we are getting now so much knobs to the programmer. It's not fun. Now, before they say, okay, figure out where the parallelize loop to get blocked. Now we say, okay, what's the format? All those things in here. So we are dealing with scheduling. Interesting thing about sparsity is there are certain things that are asymptotically better than the other things. So you can at least do a simple search and say, okay, don't do this. This is asymptotically slow. Here's a space where I actually get the fastest performance. And within that, you can search through for your architecture and stuff like that. So we are trying to do that as 2 levels in here. And I want to unify sparsity. So other part is, in my group, we did Taco, which is doing tensors. And we did Graph, we do graphs. And at 1,000 feet, they look very similar. So what's the difference between graphs and tensor algebra? Tensor algebra for me is feed forward, compute that computes on everything. Graphs is iterative. You update the graphs, you do subgraph computation, you do things go through the graph. So there's a lot more fine-grained stuff in here. But at the end of the day, both are computing on large sparse data. So we are trying to figure out how to kind of unify everything. There's kind of a one unified way of dealing with sparsity, whether it's graphs or tensors and stuff like that. That's what we are doing. Google has re-implemented the Taco in MLIR. So they have basically sparse dialect. That's basically mainly based on Taco techniques in here. And there's another country, Consite, is trying to integrate Taco into the PyData sparse ecosystem. So that is where they are going. And I will end up here. So this is just a little bit of a shameless plug. This is the kind of projects my group has been doing. So if there's anything that in here that interests, just come and talk to me. I'll take questions here. Hopefully we'll have a bigger break.
Thank you very much. Okay, so we had quite a few questions, but any more questions? Yeah, go ahead. Oh, so that they can hear.
Thanks for the talk. So in the what's next slide, you mentioned at some point that, what was it, that we need hardware support for sparsity.
Yeah.
What kind of primitives would help for that?
So this is a very interesting question. Till now, when I talk to architects, I say, your way, just give me your best vector machine, I'll be happy with. There's nothing you can do for me. So here's interesting then what happened. Think you are doing sparse matrix, sparse vector multiply. What do? You bring this huge sparse matrix into the memory. You bring the vector into the memory. Throw away 90% of the data because it's doing intersection and do the computation. Why can't you do that intersection much higher up? And also, if you look at memory, right now the memory is all random access memory. And you give the address, you get the data back. In sparsity, I want to get both address and the data back. I don't have the address in there. So memory system has no clue I'm keeping sparse data in here. Can some of this hardware understand little bit, okay, it's not, you can't do all 1,000 things, but some small thing and say, okay, I have a sparse matrix in it. So this is what I was talking to Zach beforehand also. If you have variable size data, if the memory system knows that I can have 8-bit, 16-bit, 32-bit, 64-bit data, I can have a compact representation memory. When I read it, it can expand it and give it to me expanded data. That would be so much easy. I can do much better in there. So there are things like that if memory can do and the architecture can do. If all those people do compute in memory. That means basically you're taking the entire CPU and try to do memory. That doesn't work. Just give me something to just simple union and intersection. That's very simple operation, not complicated logic. You don't need a full ALU in there, just pattern matching in there, doing in there. Something like that. can have a huge impact in there. And I'll add one more thing. As I point out, you can't take a very complex thing and divide it into binary operations, because the entire thing matters. So what that means is, right now we like to virtualize. We try to run something, put it into memory, get it back. You can't do that. You have to pipeline things. So you need to come up with some kind of pipeline. The entire operation has to get pipelined, so you're not carrying things that you're going to throw away later.
Okay, we have a question here.
Sorry for making it walk so far. Thank you for the talk, a very nice body of work. I also somewhat sympathize with your comments on the publications. 2 questions. So number one, you said you used the neural network to figure out all kind of what sparse format to choose, because you have this gigantic space. So, I mean, in this domain, using a neural network is a bit of when one is desperate, right, and cannot maybe find the right solution. But before that, did you have a deterministic solution, some smart algorithm that maybe didn't give you the optimum, but did something?
We have an algorithm. There's 2 parts there. One is certain configuration, you are asymptotically bad. Because either you have to do basically binary search, or you are computing zeros, computing values that get multiplied by zeros before. So for that, we have a very nice algorithmic way of reducing that.
Okay, so it's driven by the
asymptotic notion in there. But then the next level is all about caches, parallelism, memory system, stuff like that. The models are too complicated, and we tried to see whether we can do level by level, trying to figure things out. And at some point we realized there's no order of doing things. Everything is jumbled. And then that's where we said, okay, let's throw it to a neural network and just wash our hands and say it will find it.
But this also means if you integrate it in Python and you want to make this transparent for the user, you would actually run the neural network to come up with a format. There's no other way then.
So making it transparent is a very interesting proposition. One thing we have, because we have this online tool, what we have found is over about 3 years, there are about 1,000 different things people have plugged in there, not that many. So one thing we might be able to do is a library of known computations, and we know how to transform them. At least close computation, we can mesh something in there, or probably online database or something like that. This is my other pet peeve. The compiler should be on a cloud. We should learn from everybody else's compilation and stuff like that than redoing. How many times does the Linux kernel get compiled? I mean, it should be compiled once, and then everybody should get copy. And if you do something different, I should be able to learn from that. So part of that is how we can do. Hiding this at a higher level abstraction is a tough game, because if you make the wrong decision, you can be really, really off. Especially in this, you can be asymptotically off. So this is something we are still struggling with, trying to come up with a way. And also the part of that is all this neural network stuff is slow. So the thing about the data is, normally the compute is available to you minute you write the program. So you can do offline things, learn things, stuff like that. If the compilation is slow, people don't suffer that much. But data is now in runtime. So if I have to compile and transform and machine learn after you get data, it takes a long time to amortize that cost. You can't run it once and amortize. You are running it 100 times. So there's a lot of issues in that too. So if you have a cache, I can do a very fast lookup and run. I will be happy. But right now, you need, like, if amortize the, we'll say do matrix multiply, sparse matrix multiply. It takes about 100 of them before the cost of doing all the thing can get amortized. So,
no, very well aware. Maybe one very short question. In your generalized sparsity, you used runtime length encoding and Lempel-Sieve encoding.
Yeah.
Did you try / find applications for other types of lossless encoding, or you looked at them and you thought they are not useful really?
This is pretty new. So these are the 2 things we started. We are just still we are at it. So yes, we are looking at like the thing called packed bits encoding, where you can do run length get run, and you have normal values in there. So we have looked at that. But also we are talking to Adobe, because they have a bunch of internal encoding things supposedly good. Yes, I think we haven't reached the plateau of that. I think there'll be other things too that we have to do. Thanks.
Okay, any more questions? I guess lots of questions, which is great. As I said, welcome to the questions in the beginning. So, well, thank you very much for the talk again. Yep.